f of a does not belong to phi. Okay, so if we are writing these things, if we were writing this thing for a, we could get this. Now this implication is equivalent to its contrapositive, and the contrapositive is this. That this is a statement implying another statement. The negation of the second statement implies the negation of the first statement. Negation of the second statement is this. This implies negation of the first statement. Okay, just like that, you can write the contrapositive of this one also. That will be this. Now if you combine these two things, we simply have this. A does not belong to f inverse of phi if and only if f of a does not belong to phi. So here now we have f of a does not belong to phi, so that implies a does not belong to f inverse of phi. It makes sense. Actually the opposite now will also be true, because they are equivalent. This is true if and only if this is true. So it makes sense to write this, and this implies, so now a belongs to this and a does not belong to this. So a belongs to f inverse of u minus f inverse of phi, and so this implies what? Any element in this set is in this set. So that means this is a subset of the difference. Similarly, one can prove the converse relation. If you are well familiar with this type of arguments, you may notice that the converse argument, to prove the other thing, you will start here, right? And you can just go like this in the opposite direction. And keeping that in mind, you can, if you are comfortable with this, write like this. And that's all. That is the converse. That just proves not just this one, but this one as well. And we have equality. So this is a very compact way of proving that two sets are equal, but keep in mind it's possible in this case because everything is so easy for inverse images. Sometimes the forward argument and the backward argument will be different, will not be this straightforward. Then you cannot use these double implications and write things in such a compact and nice manner. Okay, but since we have written similarly, so we cannot use double implication. Okay, hence we now have equality. and this proves the this completes the solution. Okay, then what does the fifth one have? Let this be a function. Okay, show that so this one okay, let me just first write it. F inverse of S is equal to S for every subset S of Y if and only if F is surjective. So you can see that this is just what we already did. A few exercises back we figured this out, but it's not the same thing. That exercise, its solution where we got this thing does not automatically solve this one also, because it is if and only if. If you remember, there we said that this equality occurs if F is surjective, but if if this equality occurs, then we also have to prove that F is surjective. That we did not do there, but there is the other thing also. Also show that F inverse of F of S is equal to S for every subset S now of the domain X if and only if F is injective. Okay, and that is the second exercise, I think. Yes, the second one. So we are going to refer to that, and the solution goes like this. One half of each claim follows from the solution to the second exercise. And we prove the other halves. Okay, so that means first we have to show that if this is true, then F has to be surjective. But let us first put some more ink. First, assume that f inverse or f of f inverse of S equals S for every subset S of Y. Okay, so this is our assumption, and we have to prove that the function is surjective, it's onto. In particular, since we can take Y itself in place of S, we get this statement. We have f of f inverse of Y is equal to Y. But since it's almost looking like V. But since f inverse of Y equals X, we have f of X is equal to Y. Which implies f is surjective. Okay, how is this true? This is always true. You see, f inverse of Y is, what is f inverse of Y? It is the set of all elements X belonging to, by the definition of inverse image, such that f of X belongs to Y. Okay, but since the function has Y as its range, so every output anyway will belong to Y, irrespective of what the input is. So that means all the elements of X belong to this inverse image. In other words, the inverse image contains X as a subset. Okay, but according to this definition, the inverse image is also a subset of X, and these two containments give us this equality. So we can write X in place of f inverse of Y, and keep in mind this is true for any function f. We don't need to impose any restriction on a f. This is always true. So that's why we get fx equal to Y. And why does this imply that f is surjective? It's easy to see. Since fx equals Y, any element in the range will appear as the output of some element in the domain, and that is the definition of surjectiveness, or I mean surjectivity. So the first thing has been proved. Next, assume f inverse of f of S equals S for every subset S of the domain, and we have to prove that f is injective. But now we take a different approach. Instead of going like this by taking some particular value of S, we suppose f is not injective and arrive at a contradiction. Suppose f is not injective. Being injective means having or mapping different inputs into different outputs. Being not injective means mapping at least two different inputs onto the same output. That is something like this. same output. That tells us that f is not injective. At least two such elements can be found or has to be found for which this is happening, then f is not injective. Then there exist distinct elements x1 and x2 in the domain such that f of x1 is equal to f of x2, that is x1 is not equal to x2 but fx1 equals fx2. Let y be, I mean we are denoting this common thing by y. Okay. Then okay, now what happens if we take in place of S the set consisting of x1 and x2? If we take that, what do we get? Then f inverse of f of x1 comma x2. Let us think about this set. This type of situations may be, not maybe, are almost always confusing for everyone, no matter how well aware they are of the facts. So it's better to always draw pictures. So let us draw our familiar Venn diagram like picture. This is our x, this is y. x1 and x2 are two distinct elements in x and they are being mapped onto the same element y in y by the function f. Now we have taken this subset of x. Now for this subset, according to our assumption, I mean according to our hypothesis, this should be equal to this set because we are now replacing S by this set with two elements. Is it true? Let us see. Okay. What happens when we apply f to x1 and x2? You see, we get the same element y. So that means we have y here in this set. Okay. Now for this set, this is the set. For this set, we then again have to consider the inverse image. Now note that although we have considered things like this, where x1 and x2 are inputs and y is the output, now it may or may not happen that there are some more elements whose outputs are also equal to y. But whatever be the case, in the inverse image of this set, we will definitely have x1 and x2. Okay, but there may be more. So we can write like this. Am I getting it correctly? I think I have no, yeah, see, that's why I was not getting the thing that I wanted to get. It's not x1 and x2, sorry about this. Okay, let me draw the diagram once more. I completely forgot what I had to take. We still have x and y, and we have distinct elements x1 and x2 in x. They are being mapped by f onto the same element y. But instead of considering both of them, we are considering this singleton set. This we are putting in place of s. Okay. Now, say this is our image f of x1. This set. For this set, if we calculate the inverse image, in the inverse image, what do we have? We may have many things, right? I mean, apart, of course, x1 will be there. x1 belongs to f inverse of f of x1. Why? Simply because f of x1 belongs to this set. But at the same time, we also have x2 belonging to f inverse of f of x1. Okay, do you understand why the first one is true? Because f of x1 belongs to this. And f of x1 is nothing but y. So y belongs to this set. So that's why x1 belongs to this. But since f of x2 is also equal to y, and it also belongs to this set, x2 also belongs to the inverse image. So the inverse image will contain both x1 and x2. Keep in mind that it may contain more than these two things, because who knows, maybe there is some x3 whose image is also y. We just owing to the fact that f is not injective, it's not fact but our supposition, we have got at least two elements x1 and x2 which are distinct, but their f images are equal. There may be more. Okay, we don't need them, but there may be more. So now what can we write? Okay, see, if I write this is a superset of x1 comma x2. Does it make sense? It makes sense because you see, this is the entire inverse image. F inverse of f of x1. We already know that x1 and x2 are in this set, but there may be more, so that's why we don't necessarily have equality, we have inclusion. x1 and x2 are there may be more, but we need only this much. And okay, now we can continue our argument. Now it makes sense. First, when I took x1 and x2, it just defeats the purpose. That won't get me anywhere. Now note this. This also is a superset of x1, but it is a proper superset. Why? Because x1 and x2 are different, they are distinct, right? So if we replace s by singleton set x1, we don't have equality here. I mean, it goes against our hypothesis, and that is the contradiction. This is a contradiction and proves that our supposition is wrong. That is, F has to be injective. And this completes the solution. Okay, I lost some time